welcome again. So today's lesson will be on the chemical earth. And in the past few lessons, we've been talking about properties and bonding, and we looked at metallic bonding in the last lesson. So in today's lesson, we're actually going to concentrate now on another type of bonding, which is ionic bonding. Okay, so if you recognize this chemical, that's excellent. And if you don't, this is copper sulfate. This is one of my favorites because I like the color. It makes a really blue crystal because copper has that particular property. Okay? And the reason why it's there is because it's an ionic compound. And now we're going to see what actually an ionic compound is and how does it work. Okay? So the ionic structure. So ionic compounds are formed from the combination of a negative anion. So any ion that is negative, we call an anion, bonded to a positive cation. So positive ions we call cations. Okay, so that's probably how I'm going to refer to them through the lesson. So just to keep you aware. Now this bonding extends in 3 dimensions, forming a lattice of alternating patterns of positive and negative ions. Okay, so imagine this crystal. We've taken just looking square at it, just one slice of it. You can see that there's a negative, which is bonded to a positive, which is bonded to a negative, and so on and so forth. And if it was coming straight at you, you'd have a positive here, and then in front of that one a negative, and then in front of that one a positive, etc. in all 3 dimensions, right? And obviously there's a reason for that, because if you put 2 negatives together, they're just going to repel each other. So if you put a positive in between, they're going to all attract each other and keep everything tight. Okay? So the ionic bonds is what we call the force of attraction between them. And because each individual ion is surrounded by 6 oppositely charged ions, the electrostatic attraction is really, really strong. Okay, so let's take this guy here, okay, this one ion right here. If you actually were to put it into the lattice, you can see that it's surrounded by 1, 2, 3, 4 oppositely charged ions. But remember that this is 3-dimensional, so there'll be another ion in front, so that makes 5, and then another ion behind it that's positively charged, which makes 6 in total. Okay. And so if you imagine that you've got one ion surrounded by 6 oppositely charged ions, and then each of those 6 ions is surrounded by another 6 oppositely charged ions, that's a lot of bonds that you're making, and that's what makes it very, very strong. And that's why ionic compounds in general have a really high melting and boiling point, because when you want to separate those ions, you have to put in a lot of energy just to break up at least 6 bonds, and then probably millions more. Okay? So that's why they have such huge melting and boiling points, because the fact of the matter is that there's always going to be 6 ions surrounding a single ion all the time. Okay? So that's what makes ionic compounds very, very strong. So the question then becomes, well, how do we actually form an ion? Okay, so what actually happens? So in year 10, we looked at valency, and we looked at possibly ionic compounds as well. But in year 10, we definitely covered valency. So what happens is ions are formed when elements either donate or accept electrons from other elements or atoms. Okay? So one atom wants to give away an electron, another one wants to take in an electron. So it's sort of a match made in heaven. So when an element has an extra electron in its outer shell, it wants to give it away to achieve stability. And that forms a positive ion. Okay? Because if it gives away an electron, it lost one negative charge, but it didn't lose any positive charge. So there's more positive charges now than negative charges, so it's a positive ion. Okay? So let's just look at this guy here. It's got 3 electrons, and so that means it must have 3 protons. And if you're looking at your periodic table, you should know that this is lithium. So if it gives away one negative charge, it has now 2 electrons, but still 3 protons. So it means that it's got 1 extra proton compared to an electron, which means it must be positively charged. Okay, make sense? Now on the other hand, elements that require an extra electron to achieve a full octet, so to achieve 8 in its outer shell, or 2 depending on what it is, will take that electron and form a negative ion. Okay? So this guy here, he's got now, before he started, he had 9 electrons, so let's just ignore this yellow one here. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9. So that means it had 9 protons in its nucleus. But then we grabbed another electron, and now it's got 10 electrons, but still 9 protons. So it's got 10 electrons, 9 protons. So it must be negatively charged. Okay? And that's how we form a negative ion. Okay? So you can see here, this atom has 1 electron in its outer shell. Now, lithium, which is this guy, which is what we're going to call him, could, hypothetically, go and try and grab 7 electrons. Okay, so it could make 7 and get 8 in its outer shell, right? Could do that. But the question then becomes, is it easier to do that? See, it could just give away this electron and drop this shell completely, and then all of a sudden it's just tricked itself into thinking that it has a full outer shell. So sometimes it may be just easier to trick itself into thinking that it's got a full outer shell by getting rid of its outermost shell. Okay? So in natural science, or in chemical physics and things like that, often what happens is the easiest path is usually the one that happens. Okay? So getting 7 electrons from somewhere is difficult, but getting rid of 1 electron is very easy. So the easy path is usually the correct one. Now, in this case, this guy wants 8 in its outer shell, or it could just drop its outer shell and get 2, similar to what's happening on that side. But the problem is, in order to drop this whole shell, it has to get rid of 7 electrons. So just imagine trying to get rid of 7 electrons, or you could just, grab a new one from somewhere else. So it's easier to grab that 1 electron than to drop 7. So it will grab that 1 electron and form 8, rather than drop the shell and form 2. Okay? So that's why ions form, because it's all about getting stability, but it's just about which one's easier, which pathway is easier for it to get to that stable state. Okay? So moving away from what an ionic compound is to how we actually represent ionic compounds. So NaCl is probably the most well-known ionic compound in the world. It's, table salt. So drawing molecular or structural formula for ionic compounds isn't really logical. Okay, so remember what structural and molecular formulas were? So molecular formulas tell you how many of any particular object are in that molecule, whereas structural formulas actually have to draw each bond and each part of it. And if you imagine that the fact that a crystal could have billions of little ions inside it, then it becomes really, really impractical to draw it like in these forms. So it's what we do, and the fact is that it repeats anyway. You see always sodium chloride, sodium chloride, sodium chloride. So it'd just be monotonous to write each one. So the easier thing to do would simply be to just write the simplest repeating unit. So the simplest repeating unit is just NaCl. That's the simplest one. And that's how we represent ionic compounds. So we just represent an ionic compound as the lowest ratio of the elements inside it, okay, which is the simplest repeating unit. So in this case, it's NaCl. Easy, okay? And when we look at those, naming conventions and all that stuff that we talked about before, when you do that, the simplest ratio, we call that an empirical formula. So that's what we do with ionic compounds. We just form them as empirical formulas. Okay? It allows for a really compact representation of the ionic compound without losing any information about its structure. So it's probably the only time when empirical formulas are the preferred method, with some exceptions, of representing ionic compounds. So that concludes today's lesson on ionic compounds and ionic bonding. We looked at what an ionic compound is, what ionic bonding is, and how that forms and why it forms. So hopefully you've learned something, and so we'll move on to the question segment now. So why don't ionic compounds have delocalized electrons like metals? Okay, pretty standard question, or pretty straightforward question. When ionic compounds are formed, electrons are transferred from one substance to another. So our lithium gave one electron to our chlorine. So that electron was fully transferred to another atom. The metal gives its electron away to a nonmetal in order to achieve stability. Now these electrons will be tightly bound to the ion and thus are not free to move when ionic compounds are formed. So because the ownership of that electron has transferred, it means that now that electron is bound, it's sort of obligated to be with this new ion, and so it's not free to move and be delocalized like in a metal. Okay. Explain why ionic compounds generally have high melting and boiling points. Okay, so similar to metals, ionic compounds have very high melting and boiling points. Well, the attraction between positive and negative ions is very strong due to the large charge difference. So you've got a really big difference in charge between the positive and negative ions. Additionally, each ion is bonded to 6 oppositely charged ions that are next to it in the lattice. Okay? So 6 ions are always around. This means a large number of very strong bonds need to be broken in order for the substance to become molten. So in order for each ion to have sufficient mobility, we need to be able to break each and every one of those bonds, or at least loosen them so that they can move. And so that means that we need to put in a lot of energy, which translates into a high melting and boiling point. Okay? Ionic compounds are generally good conductors of heat, but not electricity. Why is this so? So you imagine that you've got all this charge in this crystal. Why doesn't it conduct electricity? That's just you've got all this charge, why don't you conduct electricity? Well, since the ions are closely packed to one another, the ions can easily transmit vibrations. That's why they're good at conducting heat, because the vibrations can transfer very rapidly. This means that the heat can be transferred effectively through the substance because of that tight packing. But ionic compounds have no free electrons, and the ions, which are strongly charged, can't move. They're immobile. They can't move through the lattice. And if you don't have any charge that's able to move, you don't have any current. Therefore, there is no movement of charge through the substance, making it a poor conductor of electricity, because you can't get any charge moving, which means that you don't conduct electricity. Okay? So when ionic substances are molten, they conduct electricity. However, when they are solid, they cannot. Explain what's happening. So previously, we just said that they can't conduct electricity in solid state. But when we melt them, all of a sudden, you can pass electricity through them. So what's going on? So in the liquid phase, the ions are more mobile than in the solid phase. Okay? This means that the ions are free to move under the influence of an electric field. So if you put a voltage across a molten salt, the positive ions will move towards the negative end, and the negative ions move towards the positive end because they're attracted that way. Now this net movement of charge is electrical current, so it allows the molten salt to conduct electricity. Okay, so you can see how that works. So when an ionic substance is dissolved in water, it allows the solution to conduct electricity. So why is this happening? What's the likely explanation for this? So when we actually dissolve salt in water, it actually improves the conductivity of that water. So what's going on? So when an ionic substance is dissolved in water, it is separated and surrounded by water molecules. So if we had a positive guy here, that's the other way around, sorry. What would happen is that these little Mickey Mouse water molecules would surround the positive ion and actually keep it separated from the negative ions. Okay? So now it's essentially, this unit here is free to move by itself. Okay? Now keep that in mind, that it's free to move. Now this allows ions to act as if they were in the molten state and move freely through the solution, as I mentioned. So because they're surrounded by water, they can actually drift around through the solution however they want. Now this free movement allows the solution to conduct electricity, which means that dissolving salts will allow you to improve the conductivity of water. Okay? So that concludes today's lesson on ionic bonding and ionic compounds. So we looked at how ionic bonding works, what is it, what is its structure, and where does it come from. And then in the question segment, we looked at, well, how does ionic bonding explain the properties of an ionic compound? So hopefully you can always tie those two things together, the theory and the application, and that will allow you to answer any question that you come up across in chemistry. So I look forward to seeing you at our next lesson.